Hello and welcome back to The Explainer. Today, we're going to crack a code that pretty much governs the entire periodic table. It's called effective nuclear charge, and trust me, understanding this is the key to predicting how almost any element is going to behave.
But first, let's start with a puzzle, a real head-scratcher from the world of chemistry. Think about it. As you move across a row on the periodic table, you're adding more stuff, more protons, more electrons. Logically, the atom should get bigger, right? Well, it doesn't. It actually shrinks. How on earth is that possible?
And no, this isn't a trick question. It's a totally real phenomenon. And the answer? Well, the answer reveals something fundamental about the forces raging inside every single atom in the universe.
The whole mystery really boils down to one simple fact. An electron's life inside an atom is all about location, location, location. An electron way out on the fringes feels a very different pull than one that's snuggled up right next to the nucleus. So, to really get this, we have to talk about something called the shielding effect. You can think of it like an obstacle course that gets in the way and weakens the nucleus's grip on its electrons. What's really going on is a constant battle of forces. You've got the positive nucleus trying to pull all those negative electrons in. But, and this is a big but, those electrons are also pushing each other away. The ones in the inner shells basically create this invisible force field, shielding the outer electrons from feeling the full, raw power of the nucleus. You know, here's a great way to picture it. Imagine the nucleus is a big, roaring campfire. If you're right up next to it, man, you feel that intense heat. That's kind of like an inner electron. But now imagine you're standing behind a bunch of other people. They're blocking a lot of that heat, right? You're still warm, but you're only feeling a fraction of the fire's real strength. That's an outer electron, being shielded by all the others.
Okay, so we've got this idea of shielding, this blocking effect, but in science, we can't just leave it at that. We need to put a number on it. How do we actually calculate the real pull that a shielded electron feels?
I mean, if they aren't feeling the full charge of the nucleus, what are they feeling? And the answer is this amazing concept called effective nuclear charge, or as chemists say, ZF for short. The key word here is effective. It's not the total charge of the nucleus, nope. It's the charge an electron actually experiences once you factor in all that pushing and shoving from the other electrons getting in the way.
And the formula for it is it's beautifully simple. ZF equals Z minus S. Z is just the total positive charge from the protons. That's easy, it's just the atomic number. And S is the shielding constant, which is a number that represents the total repulsive push from all those other electrons.
So the logic is really straightforward. You start with the maximum possible attraction, that's Z. Then you subtract S, which is the total amount of shielding from all the electrons that are blocking the view. And whatever is left over, that's ZF. That's the net force that electron actually feels pulling it toward the center.
Okay, so we have our tool. Now we can finally go back and solve that puzzle of the shrinking atoms. This is where it all just clicks into place.
So let's look at moving across a period, left to right. With every single step, we add another proton, so Z goes up. But here is the secret sauce. The new electron we add goes into the same outer shell. And it turns out electrons in the same shell are terrible at shielding each other. So, while that nuclear pull, Z, is getting way stronger, the shielding, S, barely budges. The result? The effective nuclear charge skyrockets, pulling that outer shell in tighter and tighter and tighter. That's why the atom shrinks. And the data just shows this perfectly. As you march along from lithium to beryllium to boron, that effective pull felt by the outermost electron just gets progressively stronger. It's like the atomic magnet is getting cranked up with every step you take to the right. So it's really that simple. A higher ZF acts like a stronger atomic magnet. It grips that electron cloud way more tightly, and that's what shrinks the atom. Mystery solved?
But ZF is so much more than just a neat solution to a size puzzle. Seriously, understanding this one concept is like having a master key that unlocks our ability to predict a whole bunch of other atomic properties.
So let's just lock in this first big payoff, right? We solved our puzzle. The link is direct. The higher the effective nuclear charge, the stronger the pull on those outer electrons, and the smaller the atom gets. This one idea explains the entire trend of atomic size across the whole table.
But wait, there's more. It doesn't stop there. Think about what it takes to actually remove an electron. We call that ionization energy. Well, if an electron is being held on by a really high ZF,
It's like trying to pull a super strong magnet off a refrigerator. It's going to take a whole lot more energy to pry that thing off. So of course, as ZF increases across a period, so does the energy you need to remove an electron. It all connects.
And this isn't just theory, This is the foundation of real practical chemistry. It's what allows scientists, as one source puts it, to comprehend and manipulate atomic behavior. This is literally how we design new molecules, new drugs, new materials, everything.
So I'll leave you with this final thought to chew on. We've seen how ZF determines an atom's grip on its own electrons. So the next logical question is, how does that internal power affect how it attracts, or repels, or maybe even shares the electrons of its neighbors? That question, my friends, is the very foundation of chemical bonding. Thanks for watching.